Um, I'll start. Yeah.
Sorry.
So good morning. Let's start the journal club. My name is Olive Cawiding, and I'm a PhD student in BioMag. And today we'll be talking about this paper called Dynamical Causality under Latent Confounders for Biological Network Reconstruction. So let's start by reading the abstract.
To USB. Oh.
Did everyone finish the reading the abstract? Okay, can anyone point out the gap sentence?
Learning.
Yeah, that's correct. Uh, the second sentence is the gap sentence. So I think for this abstract, it's the usual way of writing an abstract. You give a short background and then state the gap, and the author stated what they did to address the gap. So before we proceed, is there any opinion about this abstract or any questions? Okay, so if there is none, let's start. We begin first by defining what causality is. So intuitively, basically what causality is saying is that if there is causality between two variables, say X and Y, then X just causes Y. So that means that when you change something in X, it also changes something in Y. So this concept of causality is very obvious in several biological events. For instance, if we look at the distance walked by a person, once this increases, we know that the calories burned will also increase. And this relationship is very evident also in its time series data. So for instance, if we look at the distance walked through time, and we look at the cumulative calories burned, we can see that both are increasing. So in the case of direct causality, it can produce similar temporal dynamics. But in some cases, this is not very obvious. So for instance, if we take a look at your coffee consumption and it increases through time, and we also look at the number of hours you work through time, they are both increasing. But just looking at this time series data, can we actually say that your coffee consumption causes to increase the number of hours you work? So in this example, turns out that this is not true, and there is some other third variable that is causing both to increase. So that is your workload. Because you have a lot of workload, you consume more coffee, and you also increase the number of hours you work. And you can see that its time series is also increasing. In this case, where there is a third variable causing the increase in two other variables, but the two other variables below do not have a direct causality, we call this third variable a confounder. So even though the definition of causality is quite intuitive and seems easy, it's very difficult to establish it because usually we only have the time series data. And as you can see here, just because they behave the same, it doesn't mean that there is causality between them. So there are three main problems that are being addressed in this paper. First, how can we establish X causing Y using only time series data? The second is, how do we distinguish causality in the presence of confounding? And finally, this is one of the main problems they addressed in this paper. If the confounder data is not observed, then how can we establish the causality? So these are the three main problems that they addressed in this paper. And for each causality method, what people in this field do first is that they define what causality is mathematically. So I will show some like three example cases for causality here. Basically, they define dynamical causality by dependence on past states. So for the first case where there is a direct causality from X to Y, the equation is just this. So X is dependent on its own data, and Y is dependent on its own data and the data of X. And Z does not affect anything. And in the case of confounding, X is both dependent on itself and on a third variable Z, and Y is dependent on its own data and a third variable Z. And finally, for the case of no causality from X to Y, X just depends on itself and Y just depends on itself. So basically, if we know the underlying functions governing these dynamical systems, we can simply ask if X appears in the equation of Y. Then we can say that there is causality from X to Y. And in the paper, the way that they define dynamical causality in this original space is that X causes Y if and only if the partial derivative of Y with respect to X t minus 1 is not equal to 0. So it's easy if we know the functions, but when we deal with actual data, we don't know the underlying function. And an additional problem that we are tackling in this paper is that Z is unobserved. So the problem now is that can we distinguish these cases if we only have X and T data? So how can we learn about the underlying system if some of its variables are not observed? So this is where what we call delay embedding becomes useful. So imagine that we have a dynamical system being governed by three states, X, Y, and Z, and each point of this system is represented by these three values, X, Y, and Z in the original space. And as the time evolves, this state traces out a trajectory that is represented here. Yeah, but in reality, it could be possible that we don't know X, like some of the variables. So it turns out that, for example, we just take X, just one variable, and then we look at some delayed copies of it. So here I just took X, and then its delayed copies X t minus tau and X at t minus 2 tau. You can get more delayed copies, but I'm just showing here the case where the delay embedding dimension is p equals 3. And using these 3 time series data, I can trace out another trajectory in this 3-dimensional space. And this is what we call the state space reconstruction from X. And so the state of this system can be represented by any point in this curve. So it turns out that these two curves are equivalent. So this is the result of what we call the Taken's embedding theorem. This means that the state space reconstruction using X is diffeomorphic to the original state space. And we can do the same thing with Y also. So we get the delayed copies of Y, form this trajectory, and this curve will also be diffeomorphic to the original state space. And of course, this means that these two state space reconstructions are also diffeomorphic to each other. So the main idea that I want to emphasize here is that even when some of the variables are not observed, it doesn't mean that their information are completely lost. So because all the variables are interacting with each other, the information from the unobserved variables are somehow encoded into the temporal history of the observed variables. So now what they did in this paper is that they used the delay embedding space to define causality. So let's take, for example, this case where we have observed variables x and y. And here, the dynamics of y depends on x. So here, x causes y. And as we showed the definition earlier, this means that the partial derivative of f with respect to xt minus 1 for almost all sample t is not equal to 0. So what they did in this paper is that, please take note that here x and y are observed, but z is latent or unobserved. So what they did in this paper is they formed the delay embedding for the three variables. So we have now new embeddings for x, y, and z. And what they did is just write the equations for y in this manner. So we just transferred y to the other side and then form this matrix called H, which is a function of all the delay embeddings of x, y, and z. So this thing is just equal to 0. And if we take the determinant of the Jacobian, because we have this, because we assume that x causes y, so we know that these partial derivatives are not equal to 0, then all of the components on the diagonals will not be equal to 0. So this means this determinant is not equal to 0, and this is invertible. So the reason why we are doing this derivation is that we want to use what we call the implicit function theorem. And what this says is that if this h is 0, and if the determinant of its Jacobian is non-zero, then there exists a function f prime such that we can represent x sub t minus 1 in this way. So x sub t minus 1 is just a function of both y sub t and z sub t minus 1. But there is an obvious problem here. We know that z sub t minus 1, which is just composed of the delayed values of small z, this is unobserved. But this is where Taken's delay embedding theorem comes in. So even if z is unobserved, we know that the information of its components will be represented implicitly by the delay embedding of y. So we can simply write z sub t minus 1 to be equal to some function of y sub t. So that we can write x sub t minus 1 to be equal to f prime of y sub t and q of y sub t. So basically, we can simply express x sub t minus 1 as a function of y sub t. So this simply means that if x causes y, then there exists f such that we can write x sub t minus 1 in this way. So again, if x causes y, we can reconstruct capital X from capital Y sub t. And this is how they defined the dynamical causality in the delay embedding space. Okay, so basically, for the rest of the discussion, this will be the criteria. This equation on the right will be the criteria for establishing the causality from X to Y. Okay, now, so the question is that how do we determine if this equation is actually true? So what they did is they proved or they derived an orthogonal decomposition theorem in the delay embedding space. The proof is quite long, but I'm gonna just show the idea of the theorem. So what happens is that we have X and Y observed variables, and then we can construct the delay embedding of both variables. So these delay embeddings are in R to the P. And what the theorem says is that there exists some mapping G sub X from R raised to P to R to the M, and another embedding from G sub Y from R to the P to Rm, such that Rm here is the common latent space. So basically what G sub X and G sub Y are doing is they are mapping the delay embeddings from the delay embedding space to a common latent space, which can be decomposed in this manner. So what does this decomposition mean? This just represents Z sub X, which is information that is private to X, Z sub Y, which is information that is private to Y, and Z sub X sub Y, which is shared information between X and Y. And these subspaces are required to be orthogonal to each other. So this orthogonality just means, or this encourages that the private and the shared components will capture distinct information from each other. So there will be no overlaps. So then, because of this composition, we can write G sub X to be equal to Z sub X and D sub XY, where again, D sub X is information that can be found in X, but not in Y. And D sub XY is the shared information between X and Y. And similarly for G sub Y here, the Z sub Y is information that is private to Y and not found in X. And Z sub XY is the information that is shared between X and Y. So recall that this is what we want to establish the causality from X to Y. So then this means that if X sub t minus 1 can be constructed entirely just from Y sub t, then this means that we don't need X. So X cannot contain any private information here. And what does that mean for our decomposition? This means that if this equation is true, then Z sub X should be equal to 0. Okay, so now we can use these decompositions to distinguish different cases of causality. So we can distinguish causality, non-causality, and latent confounding. So here I'm just going to show some examples in the three-dimensional space. So for example, if we have this d sub x of x, and this is the decomposition, and let's say that the first vector is d sub x and the second one is d sub xy. This means that there is no information that is private to x. Equivalently, this means that x can be completely reconstructed from y. And we can conclude the definition of the causality from x to y. For case 2, for example, if we have this mapping and z sub x in this case is non-zero, but z sub xy is 0, then there is private information that exists that is private to x, but there's no shared information. So basically, where x is just dependent on itself, then x cannot be completely reconstructed from y. And using the same example, that means that there is non-causality. And finally, for example, if we have this mapping, the reconstruction of this vector is just this way. So both the private information in X exists, and yeah, we do the same thing for Z sub Y. So private information in Y is also existing. And finally, the shared information also exists. But we can see from these equations that neither X nor Y can be completely reconstructed from each other. So the first equation, d sub x not equal to 0, just means that x cannot be reconstructed from y. And similarly, y cannot be reconstructed from x. But at the same time, there is shared information. So that just means there is no causality between x and y, but since there is shared information, that means there is latent confounding. Okay, so now that we know that there is some decomposition of the private and shared information, this is what we use to quantify the causality between X and Y. And this is just the causality index that they introduced. So here, Z sub xy again is shared information, and Z sub x is just private to x. So you can see that this value just ranges from 0 to 1. And there are several cases here where this CIC is equal to 0 if and only if z sub xy is equal to 0, but z sub x is non-zero. And this means that there is no causality. And on the other hand, if z sub x is equal to 0, then that means that the value is 1 and there is causality from x to y. And finally, if all the components are not equal to 0, then this means that there is some latent confounding between them. Yeah, so now, so far everything has been theoretical. So we know that there is some orthogonal decomposition separating the private and shared informations of our variables. But the problem now is we don't know z sub x, z sub y, z sub xy. We cannot observe them. And we also don't know the mappings g sub x and g sub y. They only prove that these mappings exist. So now, what do we do to learn g sub x and g sub y? And can we estimate them from data? So the way that they learn the mapping is through some variational autoencoders. So basically, the idea is that we input the delay embeddings into the autoencoder. We pass it through an encoder, and this encoder gives us some latent representation of the delay embedding. And we will teach the autoencoder to separate this representation. But the thing is that, so this part is just equivalent to the G sub X mapping, and this part is equivalent to the G sub Y mapping. But the thing is, this task can also be done by ordinary encoders. They can also learn these mappings. So the question is, why do we use VAEs? So for the ordinary autoencoder, what we do is we input the delay embedding, and then it gives us some latent representation through the encoder. But here in this case, we cannot really impose structure into the resulting latent representation. However, for the VAE, what it does is it does not give us directly a latent representation, but instead it parameterizes a probability distribution over the possible latent representations. So because the structure of VAEs is in this way, before giving us a latent representation, it produces first the probability distributions for the Z, and then it samples a Z from there. So this is similarly done in the Y case. And because this is the structure of the VAEs, we can impose a structure on the resulting latent representations. And in this particular problem, this is the probability distribution that they imposed. So basically, we are separating the parameters that are assigned to each block of the latent representation. So you can see here that the covariance between d sub x and d sub xy is 0. So this encourages that the information between these two will not be overlapping. So this also means that the two are conditionally independent. So given x sub t minus 1, knowing z sub x will not give us any information about z sub xy. So basically here, the diagonal covariance here just means that we will have conditionally independent components, and the private and shared latent blocks, d sub x and d sub y, are conditionally independent. So here we just want to separate the information between these vectors. But that does not immediately mean that this is imposing orthogonality. So we have to encourage that structure in some other way. And the way that they did this is that they imposed some orthogonal constraints. So here, what we need previously is that each of the private and the shared components should be orthogonal with each other. So basically, what they did is construct this loss function where we minimize this term. And ortho of A and B just means this represents the norm of the cosine similarity. And we know here that if the vectors are pointing to the same direction or the completely opposite direction, then the value is very high. But if they are perpendicular or orthogonal to each other, then this will be 0. So that is why we want to minimize this term. So minimizing this ortho will push the latent components towards orthogonality, which is what we need. And then additionally, if you notice, we have two encoders, one for X and one for Y. And the two decompositions have Z sub XY, right? But we have different labels for them. The one for X is labeled Z sub XY to the X, and we have Z sub XY to the Y. The reason is that these two encoders don't necessarily produce the same Z sub XY. They could be very different. So these are not necessarily the same, but we want them to be in the same subspace. So we simply get the error between these two terms, and we want to minimize them. So we want to encourage that the shared latent representations will be consistent with each other. And finally, so far we've just been looking at the encoder. After producing the decompositions for the delay embedding, we just concatenate them and then put it through the decoder and then look at the final reconstruction of our input. Same thing with the encoder for Y. And now we want to test if the reproduced X and Y will be as close as our input. And this is the way that we quantify it. So it looks complicated, but basically it's just saying that given the inferred latent components d sub x and d sub xy, how well is the decoder reconstructing x sub t minus 1? So if the reconstruction is very good, then this quantity should be high, but we will minimize it later, so there is a minus sign there. So we have, so that is the reconstruction loss for X, and we have a similar term for the reconstruction loss for Y. And finally, we also have this term. This is just the KL divergence for Q and P. So basically, we are measuring the difference between the encoder's distribution from a desired prior. So we just want to make the latent space behave properly. So that is why we add this KL divergence term. And this is the regularization term for the latent space embedding. Yeah, so finally, what the VAE does, it's just combines all these loss terms in order to reproduce the inputs x and y. So for the latent representations, we impose the orthogonal loss term. And then for the shared latent representations, we just force them to be equal. And finally, we just use the usual VAE loss to ensure that we are reproducing the x and y components properly. So we just add all these terms and then we minimize the whole thing. Okay, now using the VAE means that we have learned the private and shared latent components. Now we need a practical way to quantify how much information each of the latent component carries. So the idea is very simple. We will just remove one component at a time and use the same encoder to see how much the reconstruction changed. So for example, here, we are just looking at the encoder for X. So for example, here, we try removing the private information. So we just set Z sub X to be equal to 0. We put it through the decoder, and we will get another reconstruction that is only reconstructed using the shared information. And then what we do is just we take a look at how much the reconstruction changed after removing the private information. And if this thing is 0, that means that we didn't need the private information to reconstruct the output. And similarly, we also remove the shared information. So we set z sub xy to be equal to 0. We pass it through the decoder. And we get a reconstruction this time by the private information. And then finally, we check how much the reconstruction changes when we remove the shared information. And if this thing is 0, then we didn't need the shared information for the reconstruction. So basically, everything was dependent on just the private information of Z sub X. So now, what they did is that they used these reconstruction errors to actually quantify the causality. So this is now the new CIC from X to Y. So there are different cases here. If the MSE between these two reconstructions is 0, that means that the CIC correspondingly will be equal to 1. So again, this means that we didn't need the private information of X. And that means that X causes Y. And then for the second case, in this case, the numerator will be 0 and the first term in the denominator is non-zero. So this means that the CIC will just be equal to 0 and there is no causality from X to Y. And finally, if these two errors are non-zero, this means that the CIC will be, the range will be from 0 to 1, 0 and 1 excluded. And finally, this means that X, there is no causality from X to Y and there is confounding between X and Y. But of course, our data is not perfect. The cases written above are for perfect data, but in the case of noisy data, we loosen this criteria. So they provide just a range for the CIC for determining whether there is causality, non-causality, and confounder. So I think one problem with this is that they just imposed a specific value for the thresholds. So here, what they did is just they set 0.25 as a threshold between confounding cases and non-causality, and then they imposed 0.75 as a threshold, distinguishing the confounding cases and the causality case.
Did they explain how they took this threshold?
In the manuscript, they just mentioned that they imposed this, but I think there was a long derivation in the supplementary. Yeah. Okay, so that is the whole implementation of the CIC framework. And now what they did is, of course, to test it on data. First, they tested it on this three-variable system. Here they tested for X causing Y, and then they pretend that Z is not observed. And they look at four different cases. First case is X causing Y. Second is Y causing X. And then system 3 is in the case of a confounding. And finally, for system 4, this is the case of non-causality. Then what they did is they computed the causality index for X going to Y for different situations. So for the first graph there, for increasing noise level, as they compute the causality index, you can see that only the blue line is above the threshold. So it is in the region for causality, and that is corresponding to the first system there. And the rest of the systems, which do not correspond to X causing Y, are all below the threshold. So you can see that the confounding case, system 3, is in between the high and low thresholds. And in the case of increasing coupled strength, you can see again that once the coupling strength is strong enough, they can infer the relationship from X to Y. And the rest of the other cases remain below that threshold. And finally, again, for the increasing length of the time series, if the time series is long enough, then they can infer the relationship X to Y. But you can see here that there is some limitations to the method. So in order for the causal identification to be accurate, we need a strong enough coupling strength, because if you can see, if the strength is a bit low, the CIC is below the threshold. And another limitation is that the time series should be long enough to infer the correct causality. So here, yeah, you can see that we need at least maybe around 4,000 time points for correct inference. And then they also tried to compute the correlation between the unobserved Z and the latent ZXY. So you can see here that all the rest of the other cases remain very low in correlation, but it's only the violet or the purple line that is mostly above mostly shows a high correlation. Okay, so this is what they call that, this is what they claim to be the reconstruction of the latent or the unobserved Z. But again here, first, it is robust to noise. But for the last two cases, again, we need a strong enough coupling term and sufficient data to detect the strong correlation between the latent Z and the shared information Z sub X1. And of course, they also compared the performance of their approach to 8 other causality detection methods. And they showed that they were able to accurately infer the ground truth. I think one advantage, though, of this method is that they can identify the confounding from the actual causality. Because if you look at the other graphs, it's just either yellow or blue. So yellow means non-causality and blue means causality. So they have no way of determining whether a relationship is a confounding. And finally, when they applied this approach to reconstructing the rat circadian rhythm, it shows a superiority over other methods. So what they did here is that they have 4 experiments. First, the control, so they didn't do anything in the control case. But in the 3 other cases, they perturb the data to induce some phase shift. But the thing is, even if they perturb the data, they only showed how the inferred networks change whenever there are perturbations. But the only causality they really quantified is the control case only. So they claim that it is only the control case where they have a ground truth. So letter C here is the ground truth, and then they compared it to the inferred network by the control case. And then for letter E, you can see the comparison of the AUROC of the different causality detection methods. So actually, if you're looking at it, all of them are not so strong, but at least the CIC framework has a higher value than the rest of them. And I think this is the one good result from this experiment is that they tried to detect confounding. So CIC correctly identifies the confounding in real data. So what they did is that if you can see the 3 component network there, we have BMAL, clock, and DES2. And in this small subnetwork, BMAL is a confounding. And what they did is they removed the BMAL time series, and they tried to compute the CIC between the 2 remaining components. And the value of the CIC they computed is around 0.6, which is in the range of the case for confounding. So they were actually able to detect that there is a confounding between these 2 variables. And then finally, they also computed the correlation between the confounder, BMAL, and the d sub x and d sub xy. But this is again a small limitation. They say that they can reconstruct the latent variable, but the correlation between BMAL and the z sub xy is a bit moderate. So the correlation is around 0.35, but they cite that as a limitation. There were some other experiments also for testing the CIC, but they showed the same results. So they compare it with the other causality detection methods, and they showed that the CIC is more superior than them. So finally, this is the summary of the whole framework. So this work addresses the problem of inferring causality between 2 time series in the presence of unobserved confounders. And the way they do that is they take advantage of the delay embedding, and then they formulate an orthogonal decomposition theorem to separate the effects, to separate the components of the embedding, and then they try to implement the decomposition using a variational autoencoder. And finally, after inferring the components in the VAEs, the relative amount of private and shared information was used to distinguish the 3 different cases of causality, non-causality, and confounding. So this summarizes the work in the paper, and thank you for listening. If you have any questions, please, I'll be glad.